Okay, so in our last lesson, right? Almost at the end here. This is our second to last one, by the way, of the entire season, of the entire year. So anyway, our last one we talked about what equilibrium was, and I'll review that in a second. But those ideas of reactions that go two different directions. You get the forward reaction and the reverse reaction happening at the same time, and eventually some sort of a balance is met at somewhere in the middle there, and we call those equilibrium. Well, we talked a lot in the last one about forward and reverse reactions. Well, what today we're going to talk about is the quantitative way that we can deal with that. It's math, so you might want to get a calculator out, but how do we actually deal with this as in terms of a number as opposed to just, yeah, this one's kind of forward faster or slower backwards or whatever. How do we put a number to this so we get those ideas of those relative speeds? And this is something called a KEQ, or an equilibrium constant expression. So we'll take a look at how this works today, but again, you may want to have a calculator today in order to be able to do these particular kinds of calculations. All right, so here we go. So equilibrium, we talked about the leaky bucket example in the last time, and what equilibrium is, that you've got to have a balance between two different opposing processes. So number one, you have the process of my leaky bucket of filling the bucket, right? You've got that forward reaction of putting water into the bucket, but at the same time, you're having that reverse reaction of water spilling out through the holes of the bucket, or spilling out through the holes of the bottom, whatever. So there's some sort of a balance that can be reached between those two things. And when you get to equilibrium, you get the forward rate, the amount that you're adding, is equal to the reverse rate, the amount that's leaking out. And that's kind of the important point about what those two things are. And at that point, the water level in the bucket will stay the same. You can keep adding water to it, and that bucket level inside the bucket is going to stay exactly the same each time. This is what we call equilibrium. Now imagine if we do something different, like all of a sudden we change the size of the glass that we have. Instead of using the glasses there, we use a little tiny shot glass, or we use a great big bucket to throw water in there. It's going to have a different initial forward reaction rate. That's going to change something else about how this equilibrium is going to be affected. Or imagine the opposite, that all of a sudden I put a bunch more holes in the bucket, or we have tiny little holes that are in the bucket, something along those lines. That's going to change the reverse reaction rate. And those two things are going to affect that overall balance that we had in place before. So again, with these things, we're talking about now these different types of equilibrium depending on these different balance points. How big is the forward reaction? How big is the reverse reaction? We can have all different kinds of buckets, all different kinds of glasses, all different kinds of holes, lots of different types of equilibrium. So how do we quantify that rather than just the generic, yeah, one's faster or one's slower? This is what this process is about today. So with this, that concept of lots of leaky buckets, right? There isn't just one thing that's equilibrium. Equilibrium is going to be different for every different situation. Every different reaction has its own equilibrium because every different reaction is its own bucket and its own fill rate and its own leaking rate, etc. So we've got to be a little bit careful about how we quantify these things. That each one's going to have its own particular forward rate and each one's going to have its own particular reverse rate between these two things. At equilibrium each time, yeah, those rates are going to be equal, but those initial starting conditions make a big difference in terms of where that bucket is. Is that bucket staying stable with a lot of water in it, or is that bucket staying stable with just a tiny bit of water in it? And all of those make a difference. So, like I said, every single chemical reaction is going to have, is going to have its own unique equilibrium point based on those forward and reverse reaction rates, and that's independent for each chemical reaction. Sounds like a lot to memorize. It really isn't. Luckily, there's a shortcut for dealing with all of these things. And this is something called the equilibrium constant. And this is, it sounds kind of scary at first. I guarantee you it's not. Once you get the hang of these, they're actually pretty straightforward. What the equilibrium constant says is that for any particular given chemical reaction, doesn't matter which one it is, a chemical reaction, the ratio of products to reactants, in other words, the level of fullness of the bucket, is constant at equilibrium for that reaction. Every single time, the ratio is going to be the same. So the ratio forward to reverse is the same each time because it's the same reaction each time. Each reaction will have a different constant, but each reaction will have its own single constant every single time it's repeatable. So the way we set this up is like this equation that's kind of right here. It's always going to be the concentration of products, that's what the square brackets mean, divided by the concentration of reactants. That's what we mean by a ratio. So concentration of products divided by reactants. Again, you're always using concentrations, which in the units of molarity. So that square brackets indicate that it's concentration. And again, our units is going to be that funky M that we're talking about, moles per liter. When we do this ratio has a name called the equilibrium constant. That's what we call it. We abbreviate the equilibrium constant as K with a subscript EQ. K stands for constant, because of course it's spelled with a K, but K stands for constant, and then the EQ means it's the equilibrium constant. There's lots of different kinds of constants as you get later on into chemistry. So it's the KEQ, the equilibrium constant, the ratio of products divided by reactants. And again, this is based on the balanced chemical equation. I'll show you in a second what that looks like. And each chemical equation, because it has its own chemical equation, has its own ratio. And again, it just depends on the reaction itself and the way you balance it out. Sounds a little bit weird. See a couple of examples and you see it's not so bad as it sounds, but it's called K, or KEQ in this case. So that's how you're going to write out your formula. This is what equilibrium constant expressions look like. They're KEQ, and then you've got the equal sign, and you've got square brackets for the products, concentration of the products, and square brackets for the concentration of the reactants. So that's called an equilibrium constant expression. So it's just going to look like a little equation. All right, that's what we got. I already said that. So here we go. Writing equilibrium constant expressions. It's not as hard as it sounds. Products go on the top, reactants go on the bottom. It's the ratio of products to reactants. Always uses concentrations. So when we say, like in this middle line here, brackets with C, means the concentration of C in moles per liter. It's molarity. Products on the top, reactants on the bottom. So let's take a look at this kind of fake example that I have up here for this particular little thing. So A plus B is in equilibrium with C plus D. So we would start off by writing our equilibrium expression by writing KEQ and then the equals sign. Again, products go on the top. And then we got a divided by reactants on the bottom. A couple things to take a look at here. Make sure that you multiply them together. You don't add them, you multiply them. So it's the concentration of C times the concentration of D divided by the concentration of A times the concentration of B. You've got to be a little bit careful with your calculator in terms of how you work on this. If we have coefficients in our equation, we just add one extra piece to this. So again, products on the top, reactants on the bottom, we're going to multiply them together. The only thing that makes it different is when you have coefficients out in front, the coefficients become exponents. I know it's kind of a weird leap of faith on this one. I don't really think you want me to explain why that is. I can if you really want me to. I don't think you want me to. Just trust me on this one. The coefficients become exponents. So again, here's what it looks like when you set it up. You start off with the KEQ and the equal sign. So I'm going to use this kind of longer equation. Let's pretend that it's like, 2A plus 3B equals 1C and 2D or something like that. So when we write this out, products on the top, reactants on the bottom, they're always in square brackets because it's concentrations, and our coefficients become exponents. So it kind of looks like this. So you've got the concentration of C in square brackets to the exponent, to the C power, whatever that is. It could be a 1, it could be a 2, it could be a 3. And then it's times concentration of D to the D exponent, and then divided by A to the A exponent and B to the B exponent. Like I said, we'll look at a couple of examples that will make a lot more sense. Once you get the hang of this, not so bad. So products on top, reactants on the bottom, you're multiplying, and then if you have coefficients in a balanced equation, they become exponents. All right, so what does this look like when we actually try to work all these things out, if we want to make sense out of what this is? If KEQ means products over reactants, what kind of numbers do you get for this? That's kind of the question that we've got. And again, those are two different ways to write our equilibrium expression up there on your screen. So again, these are concentrations, and what do we do with this? Ratio of products on top to reactants on the bottom. If the products is a lot, in other words, it's a forward reaction, we have a whole bunch of product being made and very little reactant that's left. That's what this case is. Products are greater than reactants. Then our value for this number math-wise is going to be greater than 1, sometimes in the thousands range. But again, if I have a whole bunch of products, my concentration is going to be like 5 molar. And I have almost no reactants left, so it's going to be like 0.01 molar or some small number. So a big number divided by a small number is going to give you a big number for your KEQ. That means that our products are favored. In other words, we made a bunch of product. It's the typical kind of reaction like you're used to. A whole bunch of products, and there's basically no reactants left at the beginning. Equilibrium means it lies to the right. Again, the products are on the right side, so the equilibrium is far over to the products side, and they're happy. And it means that our initial forward reaction rate's fast. In other words, we're making a bunch of product, and not a lot of product is falling apart. Keep in mind that the one-way reactions that we've done in class, like precipitation reactions, have KEQ values in the thousands because it's basically 100% all products, and basically you're almost dividing by 0 at the bottom. The amount of reactants that's left is so small. So again, when you see these KEQ values, they can have a huge range, but if it's greater than 1, it's the typical reaction like you're used to. It means you have a lot of products and basically no reactants left. All right, if it's the opposite, what do we get? So this is kind of the reverse from the types of reactions that we've normally done, where really the reaction wants to go the other way. We have a lot more reactant left at the end than we have product. Very little product is being made. So that means our reactants are favored. The reverse reaction is the one that's kind of going. I know it sounds really weird to say that. When the reactants are being favored, that means our equilibrium is kind of lying over on the reactant side, the left side of the equation. Again, it's just language that they use to kind of describe this. And this means that our reverse rate is really kind of winning, right? We're trying to make these products, but the products keep falling back apart into reactants. So the reverse rate from products to reactants is actually faster than our forward rate. And then these are going to have really small KEQ values. A lot of times here you can find KEQ values to the 10 to the minus 6. Very common to have like 0.000001 or something like that. Really small values. And again, what that means is, if you take a look at this, if you have a small number on the top, very little product, and a big number on the bottom, a bunch of reactant, this value is going to be really small. Like 1 divided by 1,000 is going to be 0.001. It's going to be a small value for KEQ. So those KEQ values kind of tell you which side's bigger or smaller. If KEQ is bigger than 1, that means the top part, the products are winning and the forward reaction is working. If the KEQ is really small, that means the bottom of this ratio is winning. Our reverse reaction is the one that's going a lot faster, and it's the reactants that are favored. So again, it's a little bit weird in terms of kind of seeing what these are, but it just kind of gives you an idea between the two of which one's winning. Is it going forward faster, or is it going reverse faster? Finally, would be the simple case, which doesn't happen very often, if the reactants and the products were equal to one another. If they were exactly equal, like when we were done, we had 1 molar of products and 1 molar of reactants, our KEQ would be equal to 1. It just means that at the end they're equal. Very uncommon to see that. Finally, just keep in mind, you cannot have a KEQ equal to 0. That would mean there would be 0 products that were produced, which means there's no reaction. You can't divide by 0 either. It means you can't have no reactants left. There's always a tiny bit left, so that won't work. And you can't have a negative value because there's no way to have negative concentration. How would you have like -5 moles per liter? Doesn't make any sense there. So just to check your math on there. So again, you can't have 0, you can't have negative numbers. You can have quite large values and you can have quite tiny values, so there's kind of a big range in between there. All right, here's some practice. Okay, so your brain's probably really, really full right now, like, oh my God, what am I doing? Let's take a look at a couple of these and kind of talk our way through what they are, practice problems, and this will make a little bit more sense. So we're going to write KEQs for these equations that are on there. So we're going to do, I'll lead you through the first one, then I'll say hit pause, and you can kind of try to do the other ones on your own. So here we've got a balanced equation. I believe it's balanced. 1 carbon, 2 oxygens, 2 oxygens, 2 hydrogens, 2 hydrogens. Oh yeah, it's balanced. Okay, so we're set. So what do we write this? Okay, KEQ equals products on the top, reactants on the bottom. So when I write this out, I start with my KEQ part, and then I'm going to put my products in square brackets on the top. My products are CO and H2O, so there's my general bit. Here's the one for this one. CO is on the top, it's one of my products. H2O is my other product, and it would go on the top. And then my 2 reactants are CO2 and H2, and they go on the bottom. So that's how you write those basic KEQs. So again, it's not that hard once you start to figure. Start on the right, finish on the left. So your turn. Try to do the second one. This one's got coefficients to it. So remember, coefficients need to become exponents. Go ahead and give it a shot. Okay, here we go. So KEQ for this one, products on the top, reactants on the bottom. So I've got my products on the top, N2 and H2O are my 2 products. The concentration of the H2O has to be squared because I've got a squared value right here. There's a 2 there, so that becomes my squared over here. My reactants are on the bottom. My reactants are NO and H2. Those are the left side of my equation. And in this case, each one of these is squared because I have coefficients of 2 in my balanced equation. There's my coefficients of 2 and 2. So that's why those are both squared on the bottom. Okay, bottom one, you've got to balance it first and then write the KEQ for it. Ready? Okay, here we go. So, if you're not ready, hit pause. Are you ready? Okay. Balance it first. Got to balance the equation. There should be a 2 out in front there, so the 2 is kind of funky, but I need 2 NO2s on the right to make this thing balance out. So now I can write my KEQ expression. Product goes on top. There is only one, so we can just have that one thing on top, and it is squared for my balanced equation. And then the N2O4 is on the bottom. Okay, so writing the KEQs isn't too bad. The math on this is just plug and chug. You're going to be given concentrations and start to put some numbers into your KEQs. So don't make it too crazy. I know it's intimidating at first. So products on the top, reactants on the bottom. You're multiplying across. So if you have 2 different products, and then you use coefficients or exponents. Okay. Whew. Next up, We do have certain kinds of reactions where we have different physical states that are present, and these are called heterogeneous reactions. Remember, homogeneous reactions mean they're the same physical state throughout. So like they would be all gases or all solutions. The ones that I did on the previous page were all gases. You can go look back if you want to, but trust me on this one. So with these, what's nice about them, or not nice about them, it's kind of a pain actually, the concentrations of these things can change. You can change the concentration of a solution, you can change the concentration of a gas, the amount of moles per liter. With heterogeneous reactions, it's a little bit of a kind of a trick question sort of thing. Sometimes we get the formations of solids or liquids that are also present in these reactions. Here's what's weird about these. If you have a solid, it cannot change its concentration. A solid is by definition 100% of that solid. Or if it's a liquid, it's 100% of that liquid. If it's got something in it, then it's a solution. It's not a liquid anymore. And that sounds really funny to say that. So again, with these things, what makes it a little bit easier but a little bit harder to remember is that liquids and solids, because their concentrations don't change, we don't include them in KEQs. So we leave them out. And that's kind of nice for us because at equilibrium, their concentrations cannot change. We don't need to put them in a changing concentration equation. Right? It's kind of weird. So let's take a look at an example of what I'm referring to here. When we do these, there's our general format. When we have a couple of expressions here, let's take a look at these to see what we've got. So here are some of these heterogeneous kinds of examples. Done the same way, products on the top, reactants on the bottom, but now we have to take a really close look at our physical states. So here we've got solid, here we've got solid, you've got gas and gas. I know a lot of times we've kind of gotten in the habit of ignoring those. Now it's important to really take a look. In KEQ expressions, you only include the states that can change concentrations, i.e. gases and solutions, G and AQ. So let's take a look at how we work one of these out. We'll do this top one as an example here. So take a look at all of your phases. So we've got two solids and we've got two gases. Only gases can change concentrations and solids do not. So what that means is we don't need to include either of those two solids in our KEQ expression. Or like I said, if you want to write them out and replace them with a 1, that's fine as well, but we don't have to include them. We only need to include the gases. So here's what this looks like right there. We would put our two products up on the top, and our reactants would be on the bottom, but we don't have any reactants that are included right now, so it's just divided by 1, basically, or we don't even have to do anything with it. There's no coefficients, so it's all set. So again, we don't include the ones that are solids, we just leave them out. So we only have our two products, and again, if you want to, you can have divided by 1 on the bottom if that makes you happier to kind of remember that's what's down there. Okay, your job to do the second one here. Maybe hit pause, take a look at that, and see if you can make a guess as to what that's going to look like. And I'm going to do it here in just a second. So again, look closely at the phases. All right? So with our phases, take a look at them. We've got a solid, a gas, and a liquid. Of those, the only one that actually can change concentration is the gas, the Cl2. Which means that when we write our KEQ expression, we don't have to include either the P4 or that PCl, whatever it was, on there, I can't even see it anymore, PCl3 I think it was. We don't have to include those. So there's a little bit of a trick on this. Remember, products go on the top, reactants go on the bottom. Well, we have nothing on the top, so you have to replace it with a 1 because there's got to be something up there. The reactants go on the bottom of the fraction, so you need to still have that space up there. There's nothing up there but a 1. Don't put a 0 up there. You have a 1 on the top, and then you've got your reactant on the bottom, which is Cl2, and then we've got to the exponent to the 4th power because there's a 4 in our balanced equation right there. So that's the KEQ for that second one. All right, so try the third one. See if you can do it. Again, look closely. You're going to use products on the top, reactants on the bottom. We've got exponents. Check your physical states. We've got some solids, liquids, gas. We've got aqueous. We've got all kinds of craziness going on in this one. Ready? Okay, give it a shot. All right, so here's our states. We've got a solid, so that's not going to be included. Aqueous is included. Aqueous CaCl2 is also included. The CO2 over here is a gas, so it is included. And then we've got liquid water. Liquids are not included. So when we do all this, those two can be left out of our KEQ. Products on the top, reactants on the bottom. So KEQ equals our two products, which are CaCl2 and CO2. They both have coefficients of 1, so we don't need to use any exponents. And on the bottom, we've got our HCl, which is our reactant, and it's squared because we have a 2 as a coefficient in there. So again, it's a little bit funky how to do this. Products always on the top, reactants always on the bottom. You use coefficients as exponents, and then you just got to remember to leave out some of those things. It's actually kind of nice that you can leave some things. But the solids and liquids, it's kind of a trick question. don't get included in those. Only gases and aqueous, or solutions, get included in KEQ expressions. There we go. All right, here's the math part. So if you don't have your calculator yet, now's the time. We're going to kind of put it all together. So once you've got your KEQ written, now we can use information from a problem about concentrations to be able to figure out what our concentrations are going to be at equilibrium. So you can figure out a missing concentration, or you can actually figure out the value of KEQ depending on what you need to do. So here's how these problems kind of read when you see them the first time. So what's the equilibrium constant for the following reaction, given that the equilibrium concentrations are PCl7 is 0.2 molar, Cl2 is 0.08 molar, and PCl3 is 0.04 molar. For some reason it didn't show up, but there should be that little equilibrium double arrow sign in this little spot, that little spot right there. So anyway, so there's our reaction. It is currently balanced for you. So the first step with this is to write the KEQ. You should be able to do this at this point. They're all gases, gas, gas, and gas. So everything's included. So take your moment, write the equilibrium constant expression, and then hit pause again. We'll do the math. Okay. All right, here we go. Here's your equilibrium expression. Looks like this. Our products are on the top, PCl3 to the first power, and then Cl2 is squared because of the 2 in the equation. And then our PCl, that should be a PCl7, is on the bottom down there. I guess it should be a 5. No, it should be a 7. PCl7 should be on the bottom down there. Sorry about my typo. But that's our KEQ that we're going to use for this. Again, sorry about that. That should be a 7 down on the bottom. So it's not a trick in terms of some magic thing appearing. So now that we've got that, we can plug in our values. These values that were given to you are concentrations that you can simply plug into your equation and start to solve them out. And that's actually what the next thing is. Read carefully though, make sure to plug things in the right spots. Don't just plug them in the order they're given to you in the equation. That's what I mean by check the order. So here you can see I have them plugged in. So the PCl3 is 0.04 molar, and so that's the first spot in our KEQ. Our second thing that was given to our KEQ is Cl2. Our Cl2 is given to us as 0.08 molar, so there it is. And don't forget to square it. That still needs to be there. And then the bottom thing is the 0.02, which goes on the bottom, because that was our reactant, and so that goes down there. Last part is just to kind of math, solve it. It just multiply, make sure to square things, and then divide by anything that's on the bottom. The nice thing is KEQ, when you're done calculating, because it's a ratio, has no units. So that's kind of nice. So by the time you math this thing out, that's what it looks like. 0.00128 is your calculated answer. I'm going to check for sig figs. It looks like I have 3 sig figs, 2 sig figs, and 0.80, and then 2 sig figs and 0.40. So my answer here is written in 2 sig figs. It's 1.3 times 10 to the minus 3, or 0.0013 would also work written either way. Again, no units for KEQ. So again, you're going to plug those numbers into your KEQ once you've written it, and then it's just a matter of kind of algebra at that point and solving for your math problem. So let's do a second example of this. So here's another one. Again, sorry my little thingy, double arrow thing didn't show up. I don't know why it does that sometimes. What's your equilibrium concentration of C, given the following equilibrium concentrations? So here you're given the equilibrium concentration of A is 4.5 times 10 to the minus 4. Equilibrium concentration of B is 0.23 grams because it's a solid. We're trying to find C. That's our kind of our question mark. What is that? And our concentration of D is given as 1.2 times 10 to the minus 2 moles per liter. And it gives you the value of K, or KEQ in this case, which is 2 times 10 to the minus 6. All right, so problem solving. Write your KEQ, plug in your values, and solve for the unknown. That's kind of what you're going to do on these. So, number 1, write the equilibrium expression. So take your second and see if you can do this. It's balanced for you, so figure out how to do it. There you go. Did you get the part that there was a solid that was in here? So we don't include B in our equilibrium expression. So you should have our products on top. C is squared because of the 2 in the balanced equation, times the concentration of D, which is our other product, divided by the concentration of A. And again, B is left out because it's a solid. It's a heterogeneous reaction, so it's not included. So there's our KEQ expression. Now you're just going to plug in your stuff that you're given and figure out what your unknown is. Your unknown is going to be here because you're trying to find the concentration of C. So that's our next step. Carefully plug in your values. Again, make sure you're putting them in the right spot, so just start throwing numbers in there. This is what it looks like. You're given the K, so that goes on the left because KEQ equals, and this is given to you your value of K. Our concentration of C is our unknown. That's what we're trying to find. It's going to be squared, so you've got to be careful with that. This right here, 1.2 times 10 to the minus 2, is our concentration of D, and then it's going to be divided by the concentration of A. That part about the grams of B is left out because, again, it's kind of a trick. It's a heterogeneous reaction. It's just not in there at all. And then the next part is just algebra, solve for C in this case, and figure out what it is. So here's our next algebra step. Don't forget your exponents and things like that. We get this. I multiplied both sides by 4.5 times 10 to the minus 4 to kind of move this 4.5 over here. And then I had to divide by 1.2 to get rid of that one, to move it over. So again, it's kind of that weird sort of algebra piece that I know is kind of hard for some of you guys. So I get c squared equals 7.5. Don't forget that that's c squared because I have to do one last step here. The last step is don't forget that if you have an exponent there, you have to take the square root. This is not the concentration of C. This is the squared concentration of C. So I take my square root. My final answer of that is 2.7 times 10 to the minus 4 molarity, or moles per liter. So again, don't forget that last part about taking your square root. So there you go. It's a matter of just kind of, once you've written your KEQ, plugging the numbers into the right spots in there, and then solving for whatever is missing. It's not going to be that you're going to have to solve for more than one thing. I'm never going to give you anything like crazy hard. There's just always going to be one of those things that's missing, and then you just got to figure out which one it is and solve for it. Okay, so there you go. Here's what we did in today's lesson. We talked about what equilibrium was and kind of reviewed that basic idea, the leaky bucket, right? That we've got a forward and reverse rate that are equal at equilibrium. And that depends on what those initial rates were, right? How big was the glass or the bucket that I was filling, and then how big were the holes where it was leaking out, something along those lines. That some point in time you're going to reach equilibrium, or you can if you do it right, and that there's going to be a ratio of that forward to the reverse part that's going to be consistent every single time. That consistency depends on which bucket and which glass you're using, so each reaction has its own ratio, but that ratio is consistent for each reaction every single time. That ratio is called the equilibrium constant. It's abbreviated with KEQ. And KEQ is the concentration of the products divided by the concentration of reactants. The only other couple of things that kind of throw some curveballs in there is that if you have a balanced equation with coefficients, that the coefficients become exponents. That if you have heterogeneous reactions, you got to watch out for those. You only include solutions and gases in your KEQs, and then you ignore solids and liquids if they're in there for whatever reason. And again, the last thing I guess would be to remember to multiply and not add those things because it gets a little bit weird. Then we talked a little bit about kind of what do those numbers mean. Okay, so I've got a KEQ number, so what? What does that mean? Well, if a KEQ is really, really big, that means my products are much bigger than my reactants at equilibrium, and the forward reaction is favored, or the equilibrium kind of lies to the right, that more products are going to be produced. If we get a really small KEQ value, much less than 1.0001, something like that, that means that the reactants were favored. The forward reaction is slow, and the reverse reaction is actually kind of winning, so to speak. So we end up with a lot of reactants and very little products. And again, our equilibrium here would kind of lie to the left. And then when we're doing our calculation problems at the end, don't kind of overthink these. You got to start with writing the KEQ, and then it's a matter of just plugging in the missing variables. Make sure to write the KEQ first, and then just really be careful with your algebra. Make sure that you're putting things in the right places. Make sure that you're multiplying when you should multiply and divide when you should divide. And then don't forget to do things like look for those exponents. Don't drop them, and don't forget to use them as you go through. So there you go. This is how we quantify equilibrium using something called the equilibrium expression. It sounds kind of scary. It's kind of overwhelming at first. As soon as you run through a couple of examples like we'll do in class tomorrow, hopefully it'll get quite a bit easier for you because it's really pretty straightforward once you get your kind of head around what these different things are. Okay, there you go. I will see you in class. Finals are coming. Hang in there, guys. We're almost there.